semester.
Cool. Thanks, Kira. Fran, do you want to flip to the next slide? Perfect. I will make this quick because I know everyone wants to hear from Fran. Again, I'm Rachel, Program Director for Qubit by Qubit. We are really excited to have almost 1,200 new students joining just for the second semester. So bear with us as we repeat just a little bit of information to get those new students quickly acclimated. So as a reminder, all course information is shared through Canvas. So please be on there. Please check it at least 1 to 2 times a week. We frequently post announcements after lecture or throughout the week to make sure you have the latest information. You can change your Canvas notification settings. So every time our team makes an announcement, it will send you an email. So again, if that's easier for you to manage, please play around with the settings and make sure you're getting all the information you need. We're also excited, in addition to lecture starting this week, we have labs starting this week. Labs run Tuesday through Saturday, so please attend your required lab section. You've been added to your assigned Canvas or your assigned lab section on Canvas already. You've all received information over email about if you're not in the right lab or if you're having issues accessing Canvas. So please fill out that troubleshooting form if you need our team to look at any of that. But your Zoom link is there, and some of the materials after this lecture will be on Canvas already today. And then just really quickly, we've spoken about this before, but this course is not intended to test you. It's about learning. It's about having a risk-free environment to fail. And similar, that life happens, and we know that many of you are full-time students. So we have a flexible attendance. We try to accommodate the fact that life happens. So there are 3 unexcused absences baked into your grade. So if you can't make it to a lab 1 week, it won't affect your grade, but you should plan to be there just about every week. If you switch to the next slide. On that, so a reminder that homework and attendance is required at labs. Again, just 3 unexcused absences, so the expectation is that you're there. For homework this week, it's not going to be a regular assignment. We're going to ask you to take the technical assessment that's posted on Canvas for a completion grade. We'll use this data to make sure students have learned everything we expected the first semester and get a sense of where you're at to kind of baseline how you're entering second semester. And we'll take this assessment one final time at the end of the course. So please, it's only a completion grade. The expectation is not that you're using outside resources. Just take it knowing what you know and what you learned first semester, and that'll be your assignment for this week. Also due at Sunday or on Sunday at 11:59 when homework is normally due. And then lastly, just really quickly, we know a lot of this content will be new for students, so we have many, many resources available for you. Piazza, you should be familiar with, is an online platform where you can discuss with your fellow students and our teaching assistants, get questions answered about labs or lectures or homework assignments. It wasn't as active as we expected last semester, so we've done some reorganizing to hopefully make it easier to navigate, and we really encourage students to use that as a resource. We also make office hours available from 8 a.m. to 2 p.m. every single Friday. We've shortened these hours just a little bit this semester because they weren't really active after 2 p.m. last semester. But your fellow students who are in the course, many of whom have advanced master's degrees and are really, really proficient in these topics, will help answer your questions about homework or anything else you need. And then lastly, also on Fridays, we do a homework review session every single week with a student assistant or a teaching assistant, and they'll walk you through your homework questions. And then lastly, we have a Discord server, a bit of a change from last semester. It's not required, it's totally optional if you want to be on Discord now that we have Canvas to communicate with you, but we hear a lot of fun stories about students making friends and professional connections and all sorts of great community building happening on Discord. So you are welcome to be active on there. And I think that's it. I don't want to overload you with too much information. Just remember, we have a very small team supporting a lot of students. So use the resources that have been made available to you before you email us. But again, we're thrilled to have you and excited for second semester. And with that, I will turn it over to Fran, who will be teaching today's class, for a quick introduction.
All right. Hi, everyone. I'm Fran. And for those of you who might have missed the first slide, today's lecture will be on the quantum stack and a math review of all of the fun math we went through last semester. But before we dive into today's lecture content, as Rachel mentioned, just wanted to do a brief introduction. So I'm Fran. I recently graduated from MIT with a bachelor's in electrical engineering, computer science, and physics. There, I worked at the MIT Engineering Quantum Systems Research Group. And the past 2 summers, I did internships at Rigetti Computing and Microsoft Research Quantum. During my time at MIT, I was very lucky to get to take part in teaching Amir's introductory quantum computing course, which took place over the winter term, which is how I got into teaching quantum computing and quantum information. I also did some fun outreach events with the Society of Women Engineers there. And now I'm currently a master's student at Oxford, doing a master's in statistical sciences while also teaching for Qubit by Qubit and the coding school this awesome class. So hearing that many of you are students while doing this, that's really awesome. And just note that I'm also a student, so I understand the time management and everything. So it's really awesome that you guys are managing to work this into your schedules. And so with that, let's get into today's lecture. So as I mentioned, today we'll be talking about the quantum stack, and we'll be doing a math review of all of the math concepts we talked about last semester. This will be sort of like a high-level overview of those math concepts, talking directly about their links to different concepts of quantum computing that we also foreshadowed last semester, which we'll actually be diving into this semester. So hopefully for those of you who are part of the course last semester, this will be a good reminder, overview of all of the concepts we covered, and maybe looking at the big picture will help solidify some concepts you might have not understood the direct point of. For those of you joining the class, please use this as a time to make sure that you are already comfortable and familiar with all the math we covered last semester. And if you feel that there are any gaps, I'll have labels corresponding to which lectures we specifically talked about those concepts in, so that you can go back and rewatch them before we start actually diving into applications of all that math this semester. Um, that being said, let's start off with the quantum stack, which is actually a new concept we'll be introducing today. But again, it's sort of a more high-level overview of what a quantum computer is, and we'll draw upon a lot of the concepts we discussed last semester. So speaking of last semester, our very first lecture, you might remember with Amir, was an overview of classical computing. And we learned abstractly and theoretically how computation is performed on classical computers at the logic and bit level. So specifically, we discussed binary representation and Boolean logic. That being said, we didn't actually talk about transistors or logic gates or how you actually go about constructing the computer, any of that. We just talked about these concepts theoretically and abstractly. In lecture number 2, Amir talked about quantum computing in the abstract. However, Amir, my co-instructor, he's very much a physicist, much more so than I think I'm more of an engineer or computer scientist. And so this was a fun lecture because he talked about how quantum computers work and compared to classical computers, but from a physics perspective. Specifically, he talked about qubits, quantum superposition, quantum gates, and quantum entanglement. So for any of you who are joining the class this semester, this is a lecture I would highly recommend that you watch if you haven't already, since it even if you come in with an advanced math or physics or engineering or computer science background, this really is the core of quantum computing and might be something that you haven't seen in the past. Also a good refresher for any students who were part of the course last semester. Um, so would recommend. That being said, in today's lecture, given that I am an electrical engineer and computer scientist, we're going to do a very similar lecture to that quantum computing in the abstract lecture, but think about things more from the engineering and computer science perspective. We're going to learn how the system of a quantum computer works and compare this to classical computing systems. And so to begin that discussion, I wanted to start off by discussing what the word stack means when I say quantum stack. Um, so for those of you who have taken electrical engineering or computer science courses, you might have heard the term full stack before. Usually when people say that, they refer to developers. So a person being a full stack developer. And actually, if you go to the Oxford Dictionary, look up the definition of full stack, it says that full stack means the entirety of a computer system or application comprising of both the front end and back end. So what's meant by front end and back end? Front end is what the user interacts with when they work with a computer, whereas backend is sort of all of the processing happening behind the scenes to process the input that the user gives and then generate the output that the user receives. Um, so that being said, though, developers have to be able to not only design the front end, which is the user interface, but also design the back end, which is the computer hardware, um, the software that compiles code, translates it to machine code, and all of that. And so we're going to be thinking in today's lecture about the full system of a computer, which takes input from a user, processes it, and returns an output, and how that all sort of happens. Um, And so that's sort of exactly what I've illustrated on this slide. And in order to think about how computers work, we're going to talk about different levels of abstraction. So specifically, the highest level of abstraction that we'll sort of be talking about today is the programming level of abstraction, in which a user can write Python code. And then the lowest level of abstraction that we'll talk about is sort of transistors or the computer chip, the hardware that this code actually runs on. Um, and on the right here, you can sort of see a diagram that goes through a really detailed list of the different levels of abstraction in a computer, which are sort of the building blocks and the components that we use to describe a computer when talking about a computing stack. So this whole diagram here would sort of represent a computing stack, which is the full system of all of these different components that allow a computer to work. That being said, in today's class, we're going to abstract this stack and talk about things a bit more generically, since we don't have time to get into all the details, but we're going to think about a computer as having three primary components. The highest level of abstraction for a classical computer that we'll talk about today is classical software. So you can think of this as being Python, which we actually learned last semester. The next level of abstraction is the compiler, which is essentially a unit that transforms the software we write into lower level software that can then run on hardware. So the lowest level of abstraction then will be the actual chip or hardware that does all of the processing and computation, which ultimately then gives us back our output. So to look at both the lowest and highest levels of abstraction, hardware and software side by side, I won't go into it in a lot of depth today, but there's actually a really good video by code.org that I've put in the slides in case you're curious and learning more about classical computing and these components, and I'd recommend you watch it on your own time. But just to describe generically what hardware and software is, I think you all should be familiar with it since you all probably have laptops or smartphones. Um, The hardware is sort of all of the components that either run processing, or they're like the tangible physical things that make up a phone or a computer. So some examples in the diagram on the left are circuits, chips, wires, speakers, and plugs. Um, Whereas software is the actual code that runs on these devices. So, for example, all the applications that you might have on your smartphones, those are examples of software that a coder computer scientist went and programmed. Now, the remaining component of the stack that we have left to discuss is the notion of a compiler. And so a compiler is a specially designed program that basically takes computer code, which is written in a higher level language, and usually translates it to a lower level language. Now, you might be wondering why this is important. Well, if you think back to when computers were first being invented, people weren't actually programming. They were going in at the electrical level and sending electrical signals down to the different processing units that would then perform the and or not, the Boolean logic that we learned in first semester. However, over time, people began to develop higher and higher level languages. And what I mean by that is first they started off with like machine level code, where instead of actually having to go at a lab and sort of induce the electrical currents themselves, they had devices that could induce the electrical currents, and people would just type in ones and zeros to program their code. But then over time, there was for example, the development of assembly and C. And now today, a lot of people are using Python, which is one of the highest level languages and is actually based off of the C programming language. Um, but a computer can't actually understand Python, right? When we type in print hello world, this is not a command that a computer directly understands. Remember, at the fundamental level, a computer is made up of transistors that can really only understand these zeros and ones, the electrical signals uh, that they run on. So what a compiler is doing essentially is taking this high level coding language and translating your commands into zeros and ones that the computer can actually understand, then process, and then it'll send back zeros and ones that will then get translated into an output that the user can understand. Um, so this compiler is essentially a link between the high level of software that we interact with and the low level of processing that happens on the computer. Now, why did I want to go through all of this? Well, it turns out that a quantum computer actually has a very similar stack to a classical computer. There's just a few more levels of abstraction added. Um, and so if you put the two stacks side by side, you'll see that there are a few layers which are actually pretty similar. So in the quantum computing stack, at the highest level, you have quantum software, which is the name I'm giving to the coding libraries that you use to write quantum code. So in this class, we'll actually be learning Qiskit, which is IBM's quantum programming language. However, Qiskit and a lot of these quantum software languages are built upon classical software. For example, programming languages like Python, which are what people usually interact with in the uh, classical computing stack. Similarly to a classical computer, you have a compiler. In this case, the only difference is that instead of compiling a classical code, it'll be compiling code that was written for a quantum computer, which is why I wrote quantum program compiler. Um, Next, instead of having a classical chip or device that this code gets compiled to run on, in a quantum computing stack, you actually have what's called classical control hardware. And this is hardware that is all classical. So they are electrical devices that don't make use of any of the fun quantum properties that we've talked about last year, but they're sort of a control mechanism then for the actual hardware device. And I'll illustrate soon what exactly I mean by this. So at the lowest level of the quantum stack, right, you have the quantum hardware, which is the actual quantum computing device or chip. And so here I've made a similar diagram to the one I showed before, but just illustrating what the quantum computing stack looks like. And I tried to color coordinate it to match the um, text stack on the left. So you have your quantum software, IBM Qiskit, which is powered by Python. You have then a compiler, which takes your code and translates it something into that these classical control hardware systems can understand. These classical control hardware systems then send output signals, which are what controls our actual quantum computing device. And so on this slide, I wanted to just briefly discuss how in this class over the course of this semester, we're actually going to study different aspects of the stack. So quantum software, I would say, is probably going to be our main area of focus in the sense that we're going to be programming with IBM Qiskit, which is a quantum programming language. But then, even after we introduce quantum computers and all of that, a lot of the fun that we're going to be uh, having with these quantum computers is doing things like exploring quantum algorithms, information, and protocols. Um, and these you can think about of all falling under the highest level of abstraction, which is quantum software. Uh, Classical software we explored last semester when we did our intro to Python, and we'll continue using Python, for example, when we use IBM Qiskit, and even in the lab section corresponding to today's lecture, you'll get to do some fun stuff with Python relating to mathematics. Unfortunately, in this class, we won't have time to talk much about quantum program compilation since that's a pretty math heavy field. And unrelated to a lot of the stuff we'll be emphasizing, but it is a very cool and active area of research nowadays. So I would definitely recommend that you check it out in your free time if you can. Classical control hardware, we will be exploring in our experimental quantum information processing unit, in which we'll be talking about different platforms, or I guess different control mechanisms for quantum computers. This, though, we won't discuss probably as much as we will quantum hardware, in which we'll actually talk about the different devices that people are trying to use to build quantum computers, as well as different experimental techniques for characterizing quantum devices. So again, in this class, we will in large part be focusing on this top portion, quantum software. However, we'll also be talking about quantum hardware. We'll also be exploring this actually in the upcoming lecture when we do our intro to quantum mechanics, in which you'll actually learn how uh, I guess quantum mechanics works, and this is sort of the powering factor of a quantum device that we can then go and program with our quantum software. All right, so hopefully you found that informative and you know what to look forward to this upcoming semester. With that, I wanted to do a bit of a more in-depth exploration of what all the different components of the quantum stack are. So we'll be working our way from the bottom up to the top, starting with quantum hardware. So as I mentioned, quantum hardware consists of the actual quantum device that we call the quantum computer, right? When you see those pictures of large dilution refrigerators, inside them are small quantum devices, which are where the actual computation happens in a quantum computer. And so as of right now, there's a lot of research happening regarding which types of um, physical systems we actually want to use to build quantum computers. So a lot of the research started with nuclear magnetic resonance, but nowadays people have branched into a lot of other platforms, including trapped ion, superconducting, diamond and V centers, photonics, neutral atoms, and Majorana or topological qubits. Um, this one is actually pretty interesting because this relies on a physical phenomenon that we don't actually know if it exists. So, um, but it has a lot of pros if it does work out. That being said, though, the main thing I want to emphasize right now is that as of right now, we don't actually know what the quantum transistor is. In fact, we're not even still sure to make an analogy to classical computing if we're still in the quantum vacuum tube era, so to say. We don't actually know if any platforms that people are using nowadays will be the platform that wins out in the long term. That being said, most companies right now are banking on superconducting qubits. That's actually what the lab that Amir and I worked at MIT uses. And in fact, IBM, Google, um, Intel, and a number of quantum computing startups like Rigetti Computing all use superconducting qubits. But of course, later on in the course, we'll sort of explore the pros and cons of each of these different platforms. So you'll get a better sense as to why these companies are so interested in working on superconducting qubits. To make a further analogy to classical computing, I just kind of wanted to show you guys a photo of what really old classical computers look like in comparison to relatively modern quantum devices. So on the left, I have a photo of a 1969 four-phase systems AL1 processor. So this is one of the very first microcontrollers. Whereas on the right, I have a photo of a 2017 IBM 7-qubit device. So of course, nowadays we have larger systems. Google and IBM both have 50 qubit plus quantum computing devices, but this 7-qubit device was actually the state of the art 3 years ago. As of right now, we are seeing an exponential growth in quantum devices, and hopefully that trend will continue. And within our lifetimes, there will be um, quantum computers with tens of thousands of qubits that can function analogously to classical computers we have today. And one more thing that I wanted to emphasize for quantum hardware is actually related to the IBM quantum experience. So when you go on the IBM quantum experience, there are a number of chips that you can choose from. And actually, if you dig around a bit, you can find an option which actually gives you sort of the hardware specs of the quantum devices. So, you know, if you go and buy a laptop and you're trying to figure out which one you should get, you might look at things like what the core is on the laptop or what the clock speed are. Certain characteristics of the actual hardware of the device that tell you whether the device will work faster or better than other ones. And you can actually do similar things on the IBM quantum computer. You can see the actual chip layout, the chip connectivity, um, and then different metrics about the performance of the quantum device. So each of these metrics here on the right, T1, T2, tell us about the lifetimes of the qubits on the device. Gate error, readout error tell us about the accuracy of different operations you can perform on the device, and so forth. Um, so that's another fun way that you can explore quantum hardware on your own. So now moving on, I wanted to briefly talk about what classical control hardware is. So continuing to discuss superconducting qubits, since that's what a lot of companies, including IBM, who have sponsored our course, are using. These superconducting qubits are actually controlled via microwave pulse sequences. Now, for a lot of you, that might not mean much, but as of right now, we have to use special electronic devices to send down these microwave pulse sequences. And depending on how we shape these pulses or vary their lengths, we can actually perform different quantum gates down on the quantum computer. So we basically send in a signal, and depending on the shape and length of that signal, this performs different operations on our quantum computer. Now, in order to understand why this is the case, you need to have a pretty in-depth understanding of physics and engineering and all of that. So unfortunately, we won't have time to get into it in this class, just because a lot of you have very different backgrounds. But if you do have an advanced physics engineering background and this is something you're interested in, I would highly recommend the Quantum Engineer's Guide to Superconducting Qubits, which is a big review paper published basically on how a superconducting quantum computer works and how you can control it. Um, it walks through a lot of different components of the superconducting quantum stack. Um, that being said, though, for those of you who don't want to go into this in a lot of depth, just to sort of give you a mental image of what the classical control hardware looks like, I've again made a comparison to classical computing back in the day. So on the left, I've pictured ENIAC, which is basically the first classical computer as we know of computers today. And you can see that the ENIAC computer basically fills up a whole room. There's multiple people operating it. You have a bunch of electronic devices lining the walls. And actually, if you go into a quantum computing lab nowadays, you'll see very similar control racks lining the walls. And you actually need all of these to send the signals down that control the quantum computer. So this was a photo I took at MIT before I graduated at the MIT Engineering Quantum Systems Control Room. So 1950 versus 2020, this is currently where we are, state-of-the-art quantum computing. So the next level of the quantum stack and abstraction is quantum program compilation. And again, we're not going to go into a lot of details of this, but when you hear about quantum program compilation, you should think of this as basically being the entity which takes your quantum code that you've either written on the IBM Quantum Experience or with Python and converts it into control code for all of those electronics lining the walls that then send signals down to your quantum computer. So this is the bridge between the quantum software and the quantum hardware. Now, to go into classical software, basically, I just wanted to do a very brief review of some of the Python concepts that you all learned last semester, since Qiskit, which is what we'll be using this semester, is based on Python. So last semester, in your Python lectures, you learned about variable instantiation. So that's the idea of being able to set variables to strings, integers, floats, booleans, and there's a few other types, but those are the really main ones. In terms of data structures, you guys learned what a list is and how to instantiate those, as well as manipulate them. You also learned how to define functions, which are basically chunks of code that allow you to do some sort of processing. And the nice thing with functions is that it makes it very easy to sort of repeat code and call it over and over again. And then finally, you guys learned about for loops, right? In which if you have, for example, a list of items, you can iterate through them and perform operations on all of the items in that list. And so all of these are really powerful tools. You'll be using them a lot this semester. And they're sort of the core units of Python. Now, in addition to learning about Python, some of you guys had an additional question about what exactly, for example, SciPy and NumPy are. So for those of you who actually aren't familiar with these, we won't be looking too much at SciPy for now, but actually in this week's labs, you guys will be exploring NumPy and actually seeing how it can be used to make your lives easier for all of the mathematics that we learned last semester. So eliminating some of the tedious computation that you guys had to do. But essentially, SciPy and NumPy are Python libraries for scientific and numerical computations. And what I mean when I say libraries is that these are packages of code that you can import or call, and they contain functions, objects, classes, all sorts of really useful programs that other people have written to make your life easier. So instead of you having to, for example, go and write a set of code to perform matrix vector multiplication, NumPy already has the ability to do that. So they've defined matrices and vectors, and you can easily perform a matrix vector multiplication. But for example, if NumPy didn't exist, you might have to go and write your own function to perform this basic operation. So we like libraries because they eliminate tedious work that we would otherwise have to do ourselves, and it makes it easy to then share and distribute code. Um, and so Python has a lot of different such libraries. Um, and in fact, the one that we will be using in this class, Qiskit. So Qiskit is a similar sort of library that we can use for computation. But before I go into Qiskit, I just wanted to discuss why it is that we want to use Qiskit, right? Last semester, Abe came and did a really cool demonstration where he showed off the IBM quantum experience, where you could sort of drag and drop all of these gates to construct nice quantum circuits that could then perform quantum computation. So why do we need a quantum programming language instead of just using this drag and drop interface? Well, the question that I would like to pose to you is what happens when we start needing to design really complex large circuits? So the one I had on the right is supposed to be an example of a large complex circuit, but we'll be learning about some circuits this semester, which are actually even more complicated. And as you add more qubits, they become really big. So it would just be unfeasible for someone, right, to be going and dragging and dropping these gates in a user interface. Just like, for example, when we're writing Python code, in theory, we could have someone that's going in and dragging and dropping and OR gates, doing the Boolean logic. But then it would be really slow and inefficient to actually write out algorithms or programs, which is why we developed programming languages. Um, and similarly, when we have really large scale quantum computers with tens of thousands of qubits, which might have weird connectivities, it just becomes a huge optimization problem that would be intractable for people to solve. And so that's why you have programming languages like Qiskit that basically allow you to program the equivalent of what you would be doing in a drag and drop interface, but it makes it much more um, algorithmic and a lot easier to generalize because you can do things, for example, like use for loops to repeatedly add gates into your circuit and things like that. So it makes it, I guess it automates writing quantum code. So hopefully that gave you a good sense of what the quantum computing stack is. We went all the way from quantum hardware up to quantum software. And over the course of this coming semester, we're going to be dissecting different portions of this quantum stack. Um, with that, I wanted to give you guys a chance to take a 10-minute break before we go into our math review. So I guess we'll be back at
2:52 Eastern.
2:52 Eastern. Okay, I'll write that down. All right, have a good break, and I'll see you guys in 10. All right. Hello, everyone. It's 2:52, so we're gonna get back to lecture. But during the break, a lot of you asked really great questions about the material we covered. So before we get into the math review, I just wanted to spend some time answering some of those questions. Um, so the first question that we got is, what's the difference between a compiler and an interpreter? And this is actually a bit more of a technical question. So for those of you who've never heard what an interpreter is, don't worry. But um, I'm just as a disclaimer, I'm not like much of a computer systems and engineer, so I have not in person worked much with compilers and interpreters and all of those. But my understanding is that a compiler takes um, large chunks of codes, analyzes the entirety of the code, and then converts all of that code to, for example, machine code to all be run at once. Whereas an interpreter instead looks at code line by line and individually translates each line as it goes. And so, for example, um, when people say that a programming language is compiled versus interpreted, they're referring to the fact as to whether the code uses a compiler or interpreter to then be run at the machine level. So, for example, Python is actually an interpreted language, whereas, for example, C is a compiled language. Now, usually there are a few advantages to having compiled languages in that when compiling all of the code at once, you can a lot of times sort of make it more efficient versus when you're looking at it line by line. Um, the computer can't play little tricks to make your code run faster. So then what ends up happening to make programs that are interpreted like Python more efficient? A lot of times code which is intended for performance or speed is actually written in C or a compiled language, and then put with a wrapper, like a Python wrapper around it. But again, that's all a bit technical and not very related to quantum computing. So if that didn't make sense to you, don't worry about it. But good question. Uh, so the second question we got was, what is abstraction? And I probably should have done a better job explaining this, but when I'm talking about abstraction in computing, um, I literally mean making the computation more abstract, right? So we talked about, right, how back when computers were first developed, people were literally sending electrical signals into vacuum tubes or transistors, whatever it was, to directly control the hardware. But of course, if you want to be running real large scale code that does analysis for finance or machine learning or things like those, you can't then be going and actually writing your programs at the bit or Boolean logic level, right? That would just take horrendous amounts of times. And we as people are just not good at sort of solving those types of optimization problems. So abstraction in our computing stack refers to adding sort of layers to make programming and working with a computer easier for people. So, um, for example, in our classical computing stack, basic image that we had where we had hardware, compilation, and software. Software and compilation are two added layers of abstraction on top of hardware so that the user, instead of having to go and send signals directly to the quantum devices, can actually just write a nice program which is kind of like a language of its own, that's much easier for people to understand. And then similarly, also the output of a computer, we don't get back a bunch of ones and zeros. We get something that's already been translated into strings and numbers that we as humans can read. Um, so a or a computing stack has layers of abstraction in it. The third question we got is there a Moore's law for quantum computing? So if you think back to last semester, right, we talked about Moore's law in the sense of classical computing, how um, it was predicted that the performance of computers would sort of double every year. So we would see an exponential growth in the performance of classical computers. However, in recent years, due to the fact that our computers are so optimized, our transistors are so small, we can't make them any smaller given physical quantum limitations. That we're actually believing that Moore's law is coming to an end or beginning to decline at least. Um, and it turns out that this is actually one of the motivations for building quantum computers. Now, that being said, right now, we only have very small quantum computers. The largest ones today are around 50 or so qubits. But ideally, to perform really substantial computation with quantum devices, we'll want to have quantum computers that have thousands, if not tens of thousands or hundreds of thousands of qubits. Um, and so if we had a Moore's law for quantum computing, that would be ideal. And there are already people who have claimed that there is a Moore's law for quantum computing. There's, for example, Shulkoff's law and Nevin's law, which state that there is, in fact, an exponential growth in the performance of quantum computers every year. And we are, in fact, seeing exponential growth as of right now. That being said, quantum computing hardware and technology is still very much in its infancy. So going from, for example, 4 qubits to maybe 16 or something isn't as huge of a step as then when you're at the thousands of qubits level, getting an exponential growth upon that. Um, so whether or not these laws will actually hold true will be a test for time. As someone working in quantum computing, I really hope that it will come true, but it's up to all of the researchers and maybe those of you who will go on to do research in the field of quantum computing to build the devices that will enable this Moore's law type growth for quantum computers. All right, and then moving on to our fourth question, it seemed like some of you were still kind of confused as to what exactly I meant by classical control hardware. Um, Basically, our quantum device needs certain signals to be sent from it, which require proper electronic instrumentation. So things that, for example, generate microwave pulses, which we don't have in a standard computer. So when I said classical control hardware, I meant um, hardware uh, devices you might see, for example, in an electrical engineering lab, like oscilloscopes and wave generators and things like those, which are automated, but then used to control the quantum device at the very bottom. So we have quantum devices at the bottom of our stack, which are comprised of qubits, and they're specially fabricated to leverage the physics of quantum mechanics. Above that, we have a layer of classical hardware that sends control signals down to actually operate that quantum device. Um, that being said, that control hardware, there's nothing quantum about it. Those you could find in any electrical engineering lab, um, which is why I call it classical control hardware. And so I showed you guys the photo, right, of me with my thumbs up in our lab, which was just full of AWGs, wave generators, and oscilloscopes and things like that. And so that's what a control room for a quantum computer looks like. Um, and then the last question that I wanted to answer was regarding Qiskit and Python. So someone asked if Qiskit is the only library that can be used for quantum computing. And it definitely is not. There are a ton of other quantum programming languages out. In fact, almost every major company in quantum computing has their own programming language. So IBM has Qiskit, Google has Cirq, Microsoft Quantum has Q Sharp. Rigetti Computing, where I interned, I used PyQuil. Um, and then there's a lot of startups that don't even have quantum computing devices, but they create create their own quantum programming languages. So there's definitely a ton of options out there. Uh, but the reason in this class why we're using Qiskit is, well, first of all, IBM has sponsored our course and given us access to all of their great quantum devices. So in order to access those quantum devices, we need to use their programming language. But also Qiskit has a really active educational community. So there's tons of help pages if you get stuck, and tutorials and fun things to play around with. So that's why we're using Qiskit in this course. Um, People also asked, why do we use Python? And the main reason we're using Python is, well, twofold. Qiskit is a Python-based library, so it's a library that goes on top of Python. So you need to know Python in order to use Qiskit, right? Um, the reason why we're using Qiskit is that it takes away a lot of the work that you would need to get into writing a quantum program, right? If you wanted to write a quantum program, you would have to define data structures that would enable you to store quantum states and quantum gates or operations, and then perform multiplication of those, and then construct quantum circuits and things like that. So the fact that IBM has already written this library, as well as then there's a compiler for Qiskit, right? That then takes your quantum code and compiles it to something that can actually run on the quantum computer. If there wasn't Qiskit, you would have to do that all yourself, which is why we are using Qiskit, um, as opposed to just, say, using Python and coding everything from scratch. Um, and then also, one of the reasons why we thought it would be cool to teach Python in this class is that as of right now, Python is consistently the number one used in the world for computing. And if you go on to pursue a career in STEM, you will most likely have to write code in Python at some point. So it is just a really good language to know in general. And you're way ahead of the curve if you're, for example, going to be starting in college already knowing Python. All right. All of those were really great questions. But with that, let's go into our semester one math review. Try and make sure that we finish up on time here. So as I mentioned at the start of class, right, for those of you who were in the course first semester, this will be our last discussion of pure math. Hopefully you guys had a good winter break, and this will be a good refresher for all the concepts you learned. Maybe it'll help you make some connections between the different concepts we covered, as well as link it to quantum mechanics that is to come this semester. And again, for anyone who's new to the class, just joining, this is a good chance for you to make sure that you have the proper background, and maybe if there are any holes in your knowledge, go back and rewatch some of the lectures on certain topics. We also made a point when we were teaching the math to try and discuss connections to quantum computing, quantum mechanics. Um, so I would recommend taking a look, even if you do already know the math itself. So before we get into the math, I just wanted to pull back this quote that I really love from Professor Scott Aronson, who's on our Qubit by Qubit advisory board, in which he emphasizes why math is so important for quantum computing and quantum mechanics. And for those of you who were in the class last semester, you'll remember Jay Gambetta kicking off one of our first lectures, and he was saying that linear algebra specifically is one of the most important things you should learn to get into the field of quantum computing. So let's just quickly go through this quote by Scott Aronson, and I'll highlight all of the stuff that we learned last semester, which you should recognize in this quote. So Scott said that quantum mechanics is a beautiful generalization of the laws of probability, which we discussed last semester, a generalization based on the two norm. So this is the concept of normalization that we talked about. Ignore the two and the one. Those are just a bit more advanced math concepts, but we did discuss the notion of two norm. Rather than the one norm, and on complex numbers rather than non-negative real numbers. It can study it can be studied completely separately from its application to physics, and indeed doing so provides a good starting point for learning the physical applications later. This generalized probability theory leads naturally to a new model of computation, the quantum computing model, that challenges ideas about computation once considered a priori, and that theoretical computer scientists might have been driven to invent for their own purposes, even if there were no relation to physics. In short, while quantum mechanics was invented a century ago to solve technical problems in physics, today it can fruitfully be explained from an extremely different perspective, as part of the history of ideas in math, logic, computation, and philosophy about the limits of the knowable. And this quote is actually from the introduction of quantum computing since Democritus, which is a really fun read. It's a bit advanced, but I would highly recommend it. Um, and yeah, I just love this quote because I think it really hits home as to why math is so important and why we spent so much time on it in first semester. Um, but with that, let's dive into our review of all of those different concepts we covered. And the way I'm going to go about this is I'm going to present you guys sort of a quantum big idea, a key thing to keep in mind about quantum mechanics. And then I'll present to you guys all of the equations that we learned about which relate to that concept. So, our first concept is that quantum states are represented mathematically as complex vectors. We already spoke in several labs about the notion of the block sphere. This semester we'll actually be formally introducing, defining, discussing the block sphere in a lot of depth. Um, but you guys should already have seen it and be a bit familiar with it. And it turns out that in quantum computing, quantum mechanics more generally, we can represent quantum states as vectors that have complex components. So in lecture number 3, we started off by defining the notion of a vector. We introduced vector representation and emphasized the fact that different from a scalar, which only has a magnitude, every vector has both a direction and a magnitude. And we talked about how you could calculate the direction and magnitude of a vector. Here I only put the formula for the direction of a vector in 2 dimensions because as you get to higher and higher dimensions, you just have more angles and directions you have to calculate, but it's a similar procedure. Then we talked about how you can actually go about manipulating vectors through vector addition and vector multiplication. And so hopefully these are all things that you guys are feeling comfortable, familiar with, because we're going to be doing a lot of work with vectors this coming semester, since again, all of our quantum states can be represented by vectors. Then we went on to introduce the notion of complex numbers, right? Because quantum states are not only vectors, but specifically complex vectors. And it turns out that the complex component of these vectors is really critical to quantum computing because it is what allows us to get quantum interference or constructive and destructive interference between quantum states. And so in order to define quantum or complex numbers, we had to introduce the notion of the imaginary unit. So we defined I, which is equal to the square root of -1. Remember, we did so through describing how you could solve cubic and quadratic equations, which have a sort of negative result. Um, and then, so the 2 key things to remember about the imaginary unit are that I is equal to square root of -1, I squared is -1. And from that, we were able to introduce a complex number, which has 2 different components. It has the uh, real component and the imaginary component. And then we talked about actually how complex numbers can be represented in the um, real imaginary plane as 2 dimensional vectors. Um, And so this, for example, AI plus B can be represented as AB, where our first component is our real number, and our second component is our imaginary component of our complex number. Then we went on to describe complex number manipulation. So we talked about complex number conjugation, which basically just flips our complex number about the imaginary axis, right? So if your imaginary component of your complex number is positive, it becomes negative, and vice versa. And it turns out that this is a pretty important operation, which we'll talk about a bit more later on. We also talked about complex modulus. So basically, again, thinking of complex numbers as a vector, how you can find out their length or magnitude or norm. So that's the modulus operation. And then we talked about, again, how you can do addition and multiplication with complex numbers. But we actually saw, right, that in this representation, AI plus B, performing multiplication is really tedious and has this kind of nasty expression. So this somewhat motivated the development then of complex exponentials. So to introduce this concept, we introduced Euler's formula. We didn't actually go through and do the derivation because that's pretty math intensive. Um, but we talked about basically how a real number, right, or complex numbers, sorry, you have A plus IB, your real and imaginary component, can actually be represented in this exponential form. Um, so this is a different way of sort of parametrizing your complex numbers. And again, this has a nice geometric interpretation in the real imaginary plane, where basically instead of looking things in this Cartesian form, where your real component is your x component and your imaginary component is your y component, you can think of the complex exponential form, right, as being sort of a polar representation. So I guess that's what I wrote here. And basically, this phi, which parameterizes your exponential, tells you the angle of your vector in the real imaginary plane. You can, of course, multiply it by a radius factor if you want to make your vector longer or shorter. But if there is no sort of radius or magnitude factor, we're assuming that our vector lies in the unit circle. So it has a length, magnitude, or norm of 1. Um, and so we saw that our complex exponentials have some really nice trig relationships. But then sort of the key thing that we saw that was really nice about these complex exponentials was multiplication, right? Because when you have an exponential, multiplication just corresponds to then summing the exponents. Um, and that's what makes this representation so much easier to work with. And so in quantum computing, you will most generally see uh, complex numbers instead represented in this complex exponential form. Similarly, complex conjugation simply corresponds to flipping the sign in the exponent. Um, and that comes from the fact that cosine is an even function in this expression up here, whereas sine is an odd function. And then finally, modulus is a pretty easy operation to perform in the sense that since this exponential will cancel out, basically our modulus is just any multiplicative factor in front of our complex exponential. And then finally, in our discussion of vector shape, we talked, or in our discussion of vectors, we introduced the notion of vector shape. And so when we first discussed it, it might not have made sense as to why we were talking about this notions of rows and columns. It all seemed a bit arbitrary. But we talked about how a vector can be represented as a row or column, and the transpose basically maps a row vector to a column vector or a column vector to a row vector. And that would only make sense later on, right, when we started multiplying vectors with matrices and things like that. But before we discuss that, I wanted to introduce our next quantum big idea, which was the notion of the inner product. And so we talked about the inner product mathematically, but in a quantum computing sense, the inner product actually enables us to compare quantum states and determine their orthogonality. And we will be doing in our Brockett notation, which is still to come, um, inner products all the time this upcoming semester, because as it turns out, in most quantum computing systems, you can define a basis, and that basis corresponds to different energy states in your quantum system. And those energy states are actually orthogonal to each other in a physical sense. Um, and so we'll be, of course, describing this much more in the weeks to come in our Intro to Quantum Mechanics unit. Um, but the inner product is a super, super important notion in quantum computation. And even just generally in linear algebra, the inner product is a super, super powerful tool. And we discussed sort of all of the different nice properties. It's not only a vector to scalar mapping, but also a tool for calculating vector magnitude, for normalizing vectors, for geometrically comparing vectors, and for determining vector orthogonality. So just to go through all of those equations, we can calculate the magnitude of a vector by taking the inner product with itself. Once we've calculated a vector's magnitude, we can use that to then normalize the vector. Um, and then geometrically, we can use the inner product to compare vectors, since it turns out the inner product also has um, this formula where it turns out that the inner product is just the magnitude of two vectors multiplied by the angle in between them. So if we assume that our vectors are of norm 1, or we normalize them before applying the inner product, um, the inner product directly tells us what the angle is between our vector. And if you think of the angle between two vectors as sort of a similarity measure, in which two vectors which are parallel are the most similar and two vectors which are orthogonal are the most different, this, it turns out, is a similarity measure for our vectors. And we focused in particular on three specific cases. And so it's, again, really important that you guys just know this off the top of the head, off of your head, what the inner product is for these cases of parallel, orthogonal, and anti-parallel. So just to write it out here, when our vectors are parallel, the angle between them is 0. Our inner product has a value of 1. In the case that the vectors are orthogonal, a 90-degree angle, the inner product is 0. And when they're anti-parallel, it's -1. And we saw, right, that the inner product is kind of like a dial. So when the vectors are parallel, it's 1. And as this vector moves away, as y moves away from x, the inner product decreases from 1 to 0. And then once the vector is totally orthogonal, if we continue then moving away from x, y actually becomes closer and closer to x in the sense of becoming anti-parallel. So it decreases from 0 to -1, which is a further way of telling similarity just in the opposite direction, which we can distinguish because of the negative sign. All right, so then after we discussed the notion of the inner product, we briefly talked about the notion of a linear combination. And this coming semester, you guys will be seeing linear combinations all over the place, because one of our key concepts in quantum mechanics, right, we talked a lot last semester about the notions of superposition and entanglement. And it turns out that a superposition of quantum states is just represented as a linear combination of those vectors which represent our quantum states. So last semester, right, when we gave the example of Schrodinger's cat, we talked about the cat being dead or alive. Um, and so that's a superposition state, and that's represented by a linear combination of the cat being in the alive or dead states. Um, to describe this mathematically, we started off by giving an example of a linear combination of fruits to illustrate the notion of a linear combination generally. So we can say a fruit salad is a linear combination of the different fruits it's composed of. But in terms of vectors, it has this representation. Basically, you just have vectors which are summed together, and each vector can be multiplied by some coefficient. And that's all it takes to represent a linear combination. If we're working with a linear combination that has some structure to it, a lot of times it's useful to put it into a summation notation, just so you don't have to write out the really long sum. All right, so then thinking back to quantum states being complex vectors, right? Our next quantum big idea is the notion that the coefficients in a quantum superposition are actually probability amplitudes. Um, and we only discussed probability later on in the course, but now that you guys know what probability means, I can discuss this a bit further. So um, you have the Bloch sphere here, right? And any quantum state in it can actually be represented in this form where alpha and beta are complex numbers. Um, and so it turns out that these alpha and beta terms, if you square them and you take the modulus, right, because they can be complex numbers, these actually are um, probabilities. So in the case of beta, this is the probability when you perform a quantum measurement of measuring one. Um, and as I hinted to before, the notion or the power out of making alpha and beta complex is that it actually allows us to have constructive and destructive interference um, when performing measurements of our quantum system. And that probably doesn't make much sense right now, but actually in our very next lesson, we'll be talking about the double slit experiment in which you guys will learn all about this with Amir. Um, and so the quantum big idea here, again, is that these coefficients for your single qubit case, which has two possible states, 0, 1, the alpha beta here are probability amplitudes. And when I say amplitude again, it just means that the square of that value corresponds to the probability of measuring a state. And this actually then is related to the inner product. Um, and so in order to perform the inner product and do these sorts of calculations with complex vectors, um, we needed to define a special version of the notion of transpose and inner product to work with complex numbers. So we defined the notion of the conjugate transpose, which not only flips the orientation of our vector, but again, any complex numbers in that vector, the sign of the imaginary component is also flipped. Um, and then once we defined the conjugate transpose, we were able to redefine our notion of inner product, where basically just instead of saying that our first vector was transposed, instead we take the conjugate transpose. And the reason for doing this, again, links to this notion that the coefficients correspond to probability amplitudes. And since they are probability amplitudes, right, we learned in probability that probabilities must sum to 1. So in our 2 qubit case, right, alpha square plus beta square must be equal to 1, right, because our probabilities sum to 1. Whereas if, for example, we tried to do an inner product, a standard inner product without this notion of conjugate transpose, we would see that if we tried to take the inner product between, for example, a vector in itself, and it did have complex components, we wouldn't get this relationship that it's equal to 1. Instead, we could have imaginary components in our inner product. We would, um, which isn't allowable and not what we want. And so that's the reason and the motivation for defining this alternate version of the inner product. And when we refer to an inner product this semester, we'll almost always be assuming that it is this complex inner product, since all of the quantum states will be working with our complex vectors. All right, so now moving on, our next quantum big idea is the notion that quantum operations, which perform the computation in a quantum computer, are actually represented mathematically as matrices. So one of the reasons why we use the block sphere and we like it to represent single qubits is that it makes it really easy to geometrically interpret quantum operations. Basically, quantum operations just correspond to rotations of states in the block sphere. And we'll be talking about, for example, our Pauli matrices and operations later on, which correspond to very specific rotations. But at the end of the day, you can think of a quantum algorithm or quantum process for most intensive purposes just as being a very structured or special rotation of your quantum state. And so in order to talk about quantum state operations, we needed to introduce this notion of matrices, which is how we then mathematically, not geometrically, represent them. So we introduced matrix notation, talked about how you can write them, and we emphasized the importance of matrix shape. So a matrix shape is defined as the number of rows by the number of columns. And similar to how we learned that vectors uh, could be row vectors or column vectors, you can think of a matrix as basically being a stacking of row vectors or a sequence of column vectors. There are these two different ways of looking at matrices, which then become important later on when we perform operation or mathematical operations on our matrices. So, for example, when we take the transpose of a matrix, we're taking all of those row vectors in our matrix and then flipping them to become column vectors. Or alternatively, you can think of our matrix as being a sequence of column vectors and flipping all of those column vectors to become row vectors. The matrix conjugate transpose is doing the same transpose operation, but then again, if we have any complex values inside of our matrix, also flipping the sign on the imaginary component. We then learned how to perform all sorts of different operations on our matrices, including addition, multiplication, and for multiplication, we saw, right, matrix multiplication, scalar matrix multiplication, and matrix vector multiplication. So all different types of multiplication. I know that these equations in themselves look a bit daunting. It's, I think, a lot easier to think about all these actual operations in terms of doing them out. But here are the formulas written in terms of our nice inner products, if that helps you guys out. One thing that I always like to do and emphasize when talking about matrix and vector multiplication is a nice check that you can do yourself to easily make sure that you actually are in fact working with matrices and vectors of the right shape. So remember that for all of these forms of multiplication, besides scalar multiplication, right, for matrix, and matrix vector multiplication, you can only perform those operations for matrices and vectors of corresponding shape. So in the most generic case in which you have two matrices, the key thing to remember, right, is that the inner shape, so the number of columns of your first matrix has to match the number of rows of your second matrix. If that isn't the case, then you can't actually perform the multiplication. The shapes don't line up. You'll get a nonsensical error or answer. It just isn't defined for that. So always a good thing to keep in mind and use to check yourself. You can also, after you've performed the multiplication to make sure you actually did it right, is just check that the output of the multiplication is, for example, in this case, an n by k matrix, to make sure you didn't forget or miss any components. All right, and so then in our further discussion of matrices, we also wanted to introduce one more operation which you can perform on matrices, which is the notion of matrix inversion. And in order to define matrix inversion, we had to define the identity matrix, which is just this matrix which has ones along the diagonal, zero on off-diagonal components. But the key thing about the identity matrix is that it's basically the equivalent of, in the case of scalars, to just multiplying by one, right? If I have 5, I multiply by 1, I get back 5. In the case of matrices and vectors, if you multiply by the identity matrix, you get back the same matrix or vector. And so we defined the matrix inverse to basically be a matrix that you can multiply by your matrix so as to get the identity matrix. And you can think of this as being the equivalent in the scalar case of, for example, multiplying a by 1 over a, or sometimes you can write it as a times a minus 1 to get back 1. Um, so analogous to scalar multiplication, just in this case, we define the notion of matrix inverse. And then this was important, right, in that it allowed us to solve system of equations and all of those sorts of things. All right, so now switching gears a bit, moving away from linear algebra and into the realm of probability. Our next big quantum idea is that quantum measurement in itself is probabilistic. Um, and we hinted at this a few times last semester. I just talked about it a bit, right? And we'll be exploring this in a lot more depth in upcoming lectures when we actually discuss quantum measurement in quite a bit of depth. But the basic idea, right, is if you have a quantum state, it lies, and it's, for example, in a superposition. Maybe it's half in the one state, half in the ground state, half one, half zero. Um, Once you perform a measurement, or basically observe this quantum state, it can no longer be in a superposition. It has to collapse to a classical bit state. So you'll see either a 0 or 1. But the thing is, if you, for example, were to create that quantum state over and over and over again, maybe 100 times, and measure it 100 times, you would see a probability distribution that would form over the classical bit states 0 and 1 that would then correspond to um, the probability coefficient, so the square of your probability amplitudes in your original representation. So for example, in the case that you have a 50-50 superposition, basically half the times you measure your state, you would see it land in the 0 state. Half the times you would see it land in the 1 state. This means you have a equal superposition. And so in order to describe this mathematically, we had to introduce the notion of probability. In this case, we focused a lot on sort of discrete probabilities, since we're focusing on discrete quantum mechanics. And so in order to talk about discrete probabilities, we introduced the notions of sets and how you can compare sets and operate on sets. We then introduced the notion of a probabilistic model. So basically, this is a way of mathematically describing an unknown situation, and it has two key components, right? It has a sample space, oops, a sample space and a probability law. So the sample space, remember, is just the all of the different possible outcomes that can happen in our experiment. So if our experiment, for example, was measuring the quantum state, um, let's say psi 1 over square root 2, ground state 1 over square root 2, 1 state, then our sample space would be the set 0, 1, right? We expect our qubit to, once we measure it, either become 0 or 1. And then, of course, our probability law becomes our distribution of possible outcomes if we perform repeated measurement. And in this case, since we have our equal superposition, we expect to measure each of the quantum states 50% of the time. So that's our probability law. And we gave you guys a bunch of different examples in all sorts of different contexts, but this is the quantum computing context that you are all probably the most interested in. And of course, we'll be really diving into the actual physical meaning of all of that this semester. We're leaving the math behind and now just thinking of all of this math as a tool for understanding the physics and the actual quantum computing. So if there's anything for you guys to remember about probability, it is these three axioms. These are arguably the three most important things for you to remember. So let's go through them really quick. Every probability law must satisfy the axioms of non-negativity, additivity, and normalization. Non-negativity tells us that the probability of every event must be positive. So it must be greater than or equal to 0. Basically, you can't have a negative probability. So this is a great check when you're doing math and working with complex numbers, where sometimes if you make mistakes, strange things will happen and you'll get out negative numbers. If you ever calculate a negative probability, you did something wrong. I use this check all the time in my quantum mechanics courses at MIT. I'd be in a test, I'd calculate, oh, I got a negative probability. Okay, I made a math mistake somewhere. I have to redo this computation. The next probability law is additivity, which basically tells us that the probability of two events, assuming that they're disjoint, is just the sum of their individual probabilities. And then we discussed, right, what it means for events to be disjoint. And if there's some overlap, then you have to subtract back out the intersection of those events. But the nice thing in quantum computing, right, in general, is that our states are orthogonal. Um, and so in a quantum computer, you can't ever measure both 0 and 1 at the same time. You'll either get 0 or 1 out. So usually the rule of additivity holds in the situations we're looking for. And you don't have to do any additional subtractions or trickery. And then the final, potentially most important law for you to remember is that the probability of the entire sample space must sum to 1. So all of your probabilities are positive and they have to sum to 1. And these are actually constraints that we will use when we mathematically derive the Bloch sphere and our quantum states. So again, if there's anything for you guys to remember from all of our discussion of probability, these three axioms. Um, that being said, we did go into a bit more advanced concepts in our discussion of probability. We introduced the notion of a random variable, which I emphasized repeatedly is a bit of a misnomer, right? Because our random variable is actually a function. It links events in a probability space to actual numerical quantities. And the reason why this is important is that it then allows us to define the notion of expectation and variance. Um, if you guys are familiar with Gaussian distributions, the expectation is just just the mean of our Gaussian distribution, right? And the variance, you can think of it as the spread of our distribution. And these will be super, super important in quantum computing. And we will be calculating expectations and variances of our quantum operations repeatedly in the coming semester. And the final thing we covered in our probability unit, of course, was the law of large numbers, which tells us that the average of a large number of trials should be close to the expected value and will tend to become closer to the expected value as the number of trials increases. And why is this important in the context of quantum computing? Well, we saw in a demonstration last semester, right, where I went on the IBM quantum experience, I created an equal superposition state, and I tried measuring it. And we saw that as I increased the number of measurements, the distribution at first, it was kind of noisy, right? I might have expected a 50-50 superposition between the 0 and 1 state, but then maybe saw that it was 0 70% of the time and 1 30% of the time. But as I increased my number of measurements, my distribution began converging to my true probability distribution. And by the time I was at like 1,000 or so measurements, I was at that nice 50-50 distribution of my quantum states. Um, and so this is a concept that is really important in the context of an experimental quantum computing lab, in the sense that when we run quantum circuits, quantum algorithms, we have to measure them repeatedly in order to determine what the actual distribution of our final quantum state is, assuming that it is in some sort of superposition state at the output. And actually, one of the things that we'll be talking about later in the course when we discuss, for example, Grover's algorithm, is this notion of amplitude damping. And so one of the key things to sort of aim for in designing a quantum algorithm is to cause things to constructively and destructively interfere in your algorithm nicely, so that your output actually won't have a superposition. And ideally, you'll always just land on the state that you wanted to, because that makes it a lot nicer from an experimental lab setting where you don't have to go and actually calculate the full distribution of states in a quantum computer that might have thousands and thousands of states. But I'm getting a bit ahead of myself. There's a lot of fun stuff to look forward to this semester, so let's proceed on with our math review. So the next big quantum idea is the notion of Dirac or Brocket notation. And this is how we mathematically represent quantum states. Since you guys already know it, I've actually been using it in our other math review slides beforehand. But basically, it's this nice quantum notation. Um, Essentially, it is just an alternative representation from linear algebra, right? Usually in linear algebra, you just denote your vectors as such. If you have a transpose, you represent it like that. But in Dirac notation, it's kind of nice because you'll have a vector, which you represent with a ket, and then its transpose is just represented with a bra. And so one of the reasons why people really like this, I in particular like it a lot, right, is because you can easily sort of tell the shape or what sorts of operations you're performing on your vectors. So if you have an inner product, for example, your vectors line up like this, they get closed, and this is a scalar. Whereas, for example, if you have a ket multiplied by a bra, you're actually going to get out a matrix. And so it allows you to easily identify whether you're going to have a scalar or matrix output. And the reason, of course, why we call it bra-ket notation, right, is when you're taking an inner product, you have a bra being multiplied by a ket, hence bra-ket. And so in talking about Dirac notation, again, we started by talking about it in the context of quantum states. So our quantum states are the inputs and outputs of our quantum computer. in between, we're performing quantum operations, right? Rotations on these states. Um, and so, as I just mentioned, we define the ket as simply a column vector, whereas a bra is a row vector, which corresponds to the conjugate transpose. Oh, I should have actually put little stars here, right? That's really important for when we're taking our inner products and all those sorts of things that we do perform that complex conjugation. So then we can go ahead and reintroduce our notion of superposition, right, which is just a linear combination in terms of Dirac notation as just a sum of kets multiplied by coefficients, which we remember are our probability amplitudes. Once again, the overlap of two quantum states, or the similarity of two quantum states, is calculated by the inner product, which we just said is this bra ket. Um, and then another thing that I wanted to mention is that notion of expectation that we just defined on the previous slide for probability um, is actually written like this in bracket notation. So if we're taking the expectation of some quantum operation with respect to a state, we just sandwich our matrix between two vectors. And remember, our expectation is kind of like a weighted sum where the weights in this linear combination correspond to the probability of different outcomes. So the outcome has to be a scalar, even though our input is a matrix and a vector. And then once again, emphasizing the importance of our inner product, we can say that two states are orthogonal, right? If their bracket inner product is equal to 0. And we say that a state is normal, right, if its magnitude is equal to 1. And again, we remember that magnitude is just defined as the inner product of a vector with itself. In this case, we've defined it for actual quantum states. Um, and so it'll be a lot of fun this semester. I remember one of my favorite parts of my first quantum mechanics class at MIT was getting to use all of this fun Dirac notation. And once you start doing out large linear algebra expressions, it looks pretty cool. So you can use it to impress your parents, show them all of your fun Dirac notation, and they'll think you're really fancy. Um, all right, so moving on to our next quantum big idea is now thinking and looking more specifically at the types of matrices we use in quantum computation. And it turns out that many quantum gates in quantum computing are Hermitian and unitary. For the purposes of this class, I think actually basically all of the ones we'll look at are actually Hermitian and unitary. That being said, we're making a lot of ideal nice assumptions, and the reason why I don't say all quantum gates are Hermitian and unitary is that in fact in the real world, when we're working with noisy quantum systems, assumptions that hold true in this ideal theory world don't always necessarily hold true when you have error sources which cause your states to decay and stuff. But for the intents and purposes of this class, almost everything we'll do work with is going to be Hermitian and unitary. So it's important that you guys know what it means for a matrix to be Hermitian and unitary. So in the figure here, I've once again shown a quantum gate, which we remember just corresponds to a rotation of a quantum state in the Bloch sphere. Um, Last semester, we talked specifically about poly XYZ. We showed you guys the Hadamard. You might have seen also the controlled NOT gate. But this semester, we'll be diving into what all of these gates mean in a lot of depth. And by the end of this class, you'll know all of these gates inside out and what exactly they mean for quantum computing. So that's going to be a lot of fun. Get hyped. But then mathematically, to talk about these quantum operations and gates. So as I just said, quantum operations perform the computation in a quantum computer. And we specifically mathematically introduced these three Pauli operators. And these are really, really important in quantum computing, specifically because they actually form a matrix basis for the vector space that our quantum states lie in. Now, that was a bit mathy. We'll do a recap of vector spaces and bases in just a few minutes. But by the end of this class, you'll probably have all three of these matrices memorized and by heart. And the reason why we call them poly X, Y, Z is that if you think about the three different axes, the X, Y, and Z axis of our Bloch sphere, the poly X operation corresponds to 180-degree rotation about the X axis, poly Y corresponds to 180-degree rotation about the Y axis, and poly Z corresponds to 180-degree rotation about the Z axis. In general, quantum operations have a few key properties that Amir reviewed in his lecture number 8, which are linearity, they can be composited, and that order actually really matters, right? Because when you're performing multiplication of matrices, it's not like scalar multiplication where A times B is equal to B times A. In a lot of cases, when you're multiplying matrices, if you flip their order, you'll actually get a different outcome. And so then finally, Amir talked about the notion of a matrix being Hermitian, which basically says that the matrix is in fact equal to its own conjugate transpose. And this holds true for all observable operators. So operations that we can then observe in a real world setting. And yeah, we'll explore more of the physical implications of this starting next week with our Intro to Quantum Mechanics unit. And then the next important type of matrix that Amir introduced is the unitary matrix, which basically tells us that the conjugate transpose of a matrix is actually its own inverse. So multiplying A by A dagger is equal to the identity. And it actually turns out that all reversible operations are unitary. And in a quantum computer, ideally our system is reversible so that we're not losing any information. And also, um, since in its simplest form, it's kind of just corresponding to rotations, you can actually invert all of those rotations, or in the case of controlled knobs, you can actually deduce backwards what your starting state in your input system was. That being said, in an experimental lab setting, uh, it's always hard to enforce this constraint of unitarity because information is lost and things like that. But again, we're going to discuss all of this in from more of a physics perspective in the weeks to come. Just make sure that you know these key properties, Hermitian and unitary mathematically. All right, so our next big quantum idea is that quantum states lie in Hilbert spaces. And so the Bloch sphere is in fact a Hilbert space. And remember, Hilbert spaces aren't scary. They're just vector spaces that have the notion of an inner product added on top of them. So when we say a Hilbert space, we just mean our vectors, they lie in a vector space, but we are allowed to perform an inner product on our vectors, which is the inner product we defined before. Now, in our final lecture for our math sequence, we defined the notion of a vector space. It has all of these nice properties. And we gave a few different examples, including, for example, R2, which is the set of vectors, two-dimensional vectors with real numbers, C3, which is three-dimensional vectors, which can contain complex numbers, and so forth. And then our last quantum big idea is this notion that the eigenvectors of the Pauli matrices form bases for the quantum Hilbert space, corresponding to different measurement frames. Now, there's a lot to sort of dissect here, right? Um, so this is telling us that the eigenvectors of the Pauli matrices um, are a basis, which means they span our quantum vector space, meaning that any quantum state we can create actually can be represented as a linear combination of the bases of these eigenvectors. And remember, right, we had Pauli x, y, z, each corresponding to rotations about the different axes. And it turns out that their corresponding bases, depending on which basis you use to represent your state in, when you perform a measurement, your measurement is then relative to that reference state. So usually when we talk about quantum computers, we'll be measuring in the Z reference frame. So to, for example, create an equal superposition, you'll be, for example, in the X on the x-axis in the like plus or minus state if you want to create a sort of 50-50 superposition, and things like that. So we'll explore all of this in the context of a block sphere in the weeks to come. Um, and just sort of to re-emphasize our discussion of bases. So a basis for a vector space is the set of vectors which is linearly independent and spans the space. And remember that the notion of linear independence is sort of what constrains our basis not to have too many vectors. So we can't sort of have redundant vectors. But this notion that it has to span the whole space means that the number of basis vectors must at least equal the dimension of our space. Um, and we also discussed, right, how every vector in a vector space is a unique linear combination of basis vectors given these two constraints. But remember again that every vector space can have infinitely many bases, right? Because we can define a basis and then just rotate it or scale it, and we'll have a new basis. And we can perform infinitely many rotations or scalings and things of those sorts. And then the final math concept. So I'm just about to finish. Hang in if you can, just a few more minutes. Is the notion of eigenvectors and eigenvalues. And so eigenvectors and eigenvalues are a super, super important concept in linear algebra, but more generally in all of STEM, because usually eigenvectors correspond to important modes of our system if our system can be represented in a matrix. And so mathematically, we represent it in this form. So we have some matrix A, and we say that a vector V is an eigenvector of A if multiplying A by that vector is actually just equivalent to multiplying some scalar, which is an eigenvalue, also by that vector. And so why is this important? Well, that means that our matrix vector multiplication can actually be simplified to a scalar vector multiplication. And geometrically, if there's anything for you guys to remember, it's this geometric interpretation of eigenvectors and eigenvalues. So if you have some matrix A, any eigenvector of your system, when you multiply it by A, will just end up being scaled. There won't be any sort of rotation of your vector, and that only happens for eigenvectors of your matrix. Any other vector that you multiply by your matrix, which isn't an eigenvector, will have some sort of rotation. And it turns out that this notion that your vector isn't rotating is really important in a lot of physical systems. And we'll see why in the context of quantum computing, this is so important in the weeks to come. So as I've been stating throughout this whole math review, we learned a lot of really, really cool math this semester. And for those of you who are still in high school, you're going to be super advanced when you get to your college courses coming in knowing all of this math. But in terms of this class, this semester, we're going to be diving into the wacky world of quantum mechanics. And now you guys have all the math tools you need to really understand what's going on. So get hyped because the quantum is coming. And with that, thanks everyone. Have a good rest of your weekend and enjoy your lab sections. You're going to learn NumPy. which will allow you to get rid of a lot of the tedious calculations here. So
thanks, Fran. That was fantastic. Thanks everyone for a great first lecture. A few students asked in the Q&A if we could take a photo. So please raise your virtual hand if you would like a photo for your Instagram or whatever, and we'll try to get you moved over. Just be patient. And please edit your name if you don't want your full name to show.
oh, Rachel, I'll stop sharing my screen.
Perfect. Is it working, Gabby? It's not letting me. Oh my gosh, there's 300 people. I think, yeah, I think there's so many people, it may have frozen our Zoom links. So we might have to do this in lab when the numbers are smaller, unfortunately. Let's see. We'll keep trying, but if you're trying to get onto other things with your day, feel free to drop off. There will be other photo opportunities. Zoom is not made for 10,000 student classes. Yeah, it's not working. There are a few people. If you want to put your cameras on.
Rich, I don't know if you can hear me, but mine is totally frozen.
Okay. Mine's once in a while allowing me to move someone over.
Yeah, I've been trying. I think it's because people
It's
keep
like
raising their hand. It like
can't adjust or can't catch up. Okay, if you don't currently have your hand raised, please don't raise it. Sorry for the technical challenge. Is there a way to change this to a webinar, Gabby, so people are able to switch over?
I don't think we can do it live.
Mid-event, okay.
Yeah.
Appreciate everyone's patience. And if you can't get in ultimately, please share a selfie on social media and we will be sure to amplify that instead. But we'll try to get as many people as we can. Akshay, while we do this, would you like to introduce yourself since we didn't get a chance for that? And I know many people don't get to see you every day.
Yeah. Hey, everyone. My name is Akshay Agarwal, and you might have seen me answering questions in the chat. So I'm going to be the head TA for this class. Some of you I'll see in the lab. But yeah, very excited to see everyone and keep sending those questions in, and I'll keep trying my best to answer as many as I can.
yeah, Akshay is the one who collected all the questions during the break. He does a really good job of monitoring. And if you get your question answered, it's probably because of him. So Akshay's great.
Yeah, someone called him a machine today, which I think is a very accurate description of Akshay during lecture.
I exist in a state of answering and not answering questions simultaneously.
I've also opened up the chat if folks want to chat amongst themselves while we do this. Lots of appreciation for Akshay. Now that we know so many folks are interested in photos, we can also make this kind of a regular thing with smaller groups as the semester goes on. How about we'll get a photo with the folks who are on camera right now, and then you all can leave and we'll cycle through like wedding photos. How's that sound? All right. So if you're on screen right now, if you could turn your camera on and make sure your name is edited just to anything you're okay with being shared on social media. You have some folks along the bottom. If you could put your cameras on, perfect. All right. Okay, if I could get a smile on 3. Thumbs up if you want. Number 1 finger for first lecture, whatever you're looking at. All right, 1, 2, 3. Big smiles. Yay. Let me get the other side. 1, 2, 3. Awesome. All right. If you folks want to drop off, then we'll